This is the fourth part of our discussion on harmonic functions. So far, we have defined what are harmonic functions, and we have seen some simple examples of them. And we also discussed the relationship between analytic functions and harmonic functions. Now, as I have mentioned earlier on as well, that these harmonic functions are very important in applied mathematics. Okay, so they appear in many applications, many solutions of different real life problems. Now, in this discussion, we are going to discuss one such problem of fluid flow. Now, before going to the problem, let's recall ourselves what are harmonic functions. So, a given real valued function h of two variables x and y is said to be harmonic in a given domain D of the xy plane if, so there are two conditions. Number one, its first and second partial derivatives must be continuous. So, first and second order partial derivatives are continuous, and secondly, it must satisfy the following partial differential equations. Okay. So, now we are going to discuss a very particular fluid flow problem where the information and the knowledge of these harmonic functions are going to solve, are going to help us in solving this problem of fluid flow. Okay. So, let's see what is the physics of this problem. So, we are given the flow of incompressible and frictionless fluid flow. So, when we say incompressible, it means it cannot be compressed. In other words, the density with respect to time remains constant, or density does not change with time. Okay, and it's frictionless. In other words, when the fluid flows, then its friction with the walls is zero. Okay, so the fluid is flowing in a very deep channel. Okay, so this is a very deep channel. Okay, and the fluid is flowing inside this. So this is the physics of the problem, and we also assume that this channel is placed parallel to the complex plane. Okay, so somewhere over there, this is the complex plane. And we also assume that when we take cross sections of this channel, okay, so for example, if we take cut from here, okay, so if we take cut from here, then the cross section, so all the cross sections are same. So these are the assumptions under which we are going to study this physical problem of fluid flow. Okay, so if we discuss that, then this one of the cross section becomes this, and now since we assume that the channel is placed parallel to the xy plane or the complex plane, so we can say that this portion cross section lies inside the complex plane. Okay, so it is somewhere in the complex plane. So let's say this is the origin, and this is the real axis, and this is imaginary axis. Okay, so the real axis and imaginary axis. Now we want to discuss the motion of this fluid, which is incompressible and frictionless. And this is one cross section of this fluid. Okay. Now we want to discuss this velocity vector. So what is a velocity vector at a point xy? Now it is given as p of xy plus iota q of xy. Now what does this represent physically and geometrically? So let's say we are in a complex plane and we are given this v of xy. Okay. If we choose a point, let's say this very particular point with this scale. Okay, so let's say this is 2, 1. Okay, so this point 2, 1 in the complex plane. This is the real axis, and this is imaginary axis. Okay, so if we calculate the value of v to 1, then it is going to give me some real and imaginary part. So let's call it, for example, u1 plus iota u2, where u1 and u2 are real numbers. Okay, so these are real numbers. Now, since it's a complex number, so we can represent it with some vector. Okay, so let's say this is the vector, and this arrowhead has the components u1, u2. Now, since the velocity, we want to calculate the velocity at point 2, 1, and this vector has its tail at the origin. So we replace, or we translate this vector, okay, to this position. Okay, so we translate this vector to this position. So that's how we get velocity at any point. Okay, so in this particular example, we discussed how to find the velocity vector at this point 2, 1, and similarly we can calculate the velocity vector at any other point as well. Okay, so in other words, this velocity vector is going to give me the velocity at each and every point in the domain of the problem. Okay, so it's going to give me an arrow at each and every point in the domain of the problem. So in other words, we are going to get a situation like this. So these are the velocity vectors. Okay, so these are the velocity vectors and they are obtained from this function. Now to solve this problem, we further assume that the flow is irrotational. So in other words, there are no rotations in the flow, or the curl of this velocity vector field is 0. Now how to calculate this curl? We know that nabla is basically equal to partial by partial xi plus partial by partial yj plus partial by partial zk. Now we are in 2 dimensions, so in other words, there is no third component and we are not interested in the third components, and we also write down this v of xy in real and imaginary parts, but if we follow this notation of ijk, then we can also write it down v of xy as, okay, so p of xy I plus q of xy j, and of course the k component is 0. And with these notations, we can now calculate what is nabla cross v. So this is basically equal to ijk and partial by partial x, partial by partial y, and partial by partial z. So this is going to be equal to p, q, and 0. So this is going to give me the following expression. So the I component, so the partial by partial y of 0 is 0, and partial by partial z of q, this is also 0 because there is no component of q in the z direction. Okay, and there is no change of q in the z direction. Similarly, j becomes, so partial by partial x of 0, which is 0, and partial by partial z of p. So this is also 0 because there is no movement in the direction of z. Okay, so these components are already 0. Now what about the third component? The k component is basically qx minus py. Okay, so qx minus py k. Now these 2 components are already 0, and if we want that this flow is irrotational, then qx minus py must be equal to 0. So qx minus py equal to 0. So this is the condition on the components of this velocity vector field, that qx must be equal to py. And the next condition that we impose on the fluid flow is that there is no source or sink. So in other words, the divergence of this vector field is going to be equal to 0. And this imposed the following condition, that px, okay, plus qy must be equal to 0. In fact, we are just calculating the dot of partial by partial xi plus partial by partial yj plus partial by partial yzk, and we are taking the dot product of this with p plus iota q, and we can also write it down in the ijk form as pi plus qj plus 0k. Okay, so when we take this dot product, then this becomes partial by partial x of p plus partial by partial y of q must be equal to 0. So this is the second condition on the components of this velocity vector field, that must be irrotational and there is no source or sink of the fluid. Now we are given these 2 conditions. Now they are very similar to the Cauchy-Riemann equations, but they are not exactly the Cauchy-Riemann equations. So for example, for this complex valued function v of xy, if we say that what are the Cauchy-Riemann equations for its real and imaginary part, then they become px must be equal to qy and py must be equal to minus qx. But these conditions are not exactly these conditions, but they are somehow related to them. Okay, so in fact there is a difference of negative. So how do we construct an analytic function from these two conditions? So the next function is the answer. So if we take the real and imaginary parts to be p of xy minus q of xy. So if we take, instead of plus iota q of xy, instead of that we take minus iota q of xy, then these two conditions are the Cauchy-Riemann equations for this function f of xy. And what is the relationship between this new function f of xy and the previous complex valued function v of xy? So this is the relationship between them, that v of xy is equal to the conjugate of this f of xy. And this f of xy satisfy the following Cauchy-Riemann equations. Okay, so ux must be equal to vy and uy must be equal to minus vx. Okay, so these are satisfied because here, okay, so here u is equal to p and v is equal to minus q. Okay, and let's try to see that why this first Cauchy-Riemann equation is satisfied. So over here ux is equal to px. Okay, and we also know that px is equal to minus qy. Okay, so this is equal to minus qy, and since v is equal to minus q, so this implies that y is equal to minus qy, and minus qy is equal to vy. So that's why the first condition is satisfied, and similarly we can check that the second condition is also satisfied. Similarly can be checked. Okay, so this function f of xy satisfy these Cauchy-Riemann equations. Now let's recall what is the exact condition that a function is differentiable. Okay, so the exact conditions are its real and imaginary parts have continuous first order partial derivatives and the Cauchy-Riemann equations are satisfied. Okay, so if these two conditions are satisfied, then the function is differentiable at that point. But in this case the function only satisfy the Cauchy-Riemann equations, and so we impose another condition that, okay, so we assume that p and q have continuous partial derivatives. Okay, so so far we have imposed many conditions to arrive at a solution of this real life fluid flow problem, and this is going to be another condition on the components of this velocity vector field. Okay, so if these conditions are satisfied, then this implies that f of xy is analytic. So because p x is equal to minus qy and py is equal to qx, so this holds at each and every point in the domain of the flow of this fluid. So that's why in the whole domain these conditions are satisfied. So that's why in the whole domain f of xy satisfy these conditions, and we also assume that p and q have continuous partial derivatives in the whole domain of our discussion. So if it is differentiable at each and every point in the domain, so this implies that the function is analytic. Okay, so in domain, so of course we discussed or we consider some open set of the portion of the fluid. Okay, so this implies that this function f of xy is basically an analytic function. Now if this function is analytic, and we also have the following relationship, v of xy is equal to the conjugate of f of xy. Okay, now we want to find, okay, so we want to find a function phi of xy such that the gradient of that phi is equal to v of xy. Okay, so in other words, we want to find the potential of this velocity vector field. So to calculate that, we are going to need effect from the future, that if we are given an analytic function, then it has an analytic antiderivative. Okay, so analytic functions have analytic antiderivatives. So we are going to prove this fact in future. Now let's use this fact over here. So we know that this f of xy is analytic function, so it must have this analytic antiderivative. So there exists this capital F of xy such that when we take the derivative of this capital F of xy, then it gives us f of xy. Okay, and since it's a complex valued function, so let's assume that it has the real part as phi of xy and imaginary part as psi of xy. Okay, and from this fact, this capital F of xy is analytic functions. Okay, now we also know that if a given function is analytic, then its real and imaginary components are harmonic functions. Okay, so that's why this capital F of xy has the components phi and psi, and these are harmonic functions. Okay, because this is antiderivative of analytic function small f of xy, and this must be satisfied. This is one of the Cauchy-Riemann equations that we are going to use in our further discussion. Of course, the second condition is also satisfied, that phi x is equal to psi y. But we are not going to use this in our further discussion. So we only consider this Cauchy-Riemann equation. So why this holds? Because this capital F of xy is analytic function. So its real and imaginary components satisfy this condition. Now let's see how this is going to help us in finding the potential. So what is the gradient of this phi? So gradient of phi is phi x plus iota phi y. And what do we know about phi y? This is equal to minus iota psi x. Okay, so this becomes this using this condition. Okay, and what does this imply? So this is the conjugate of phi x plus iota psi x. Okay, and this is in fact the derivative of f, capital F of x y. Okay, and what is f prime of capital F prime of xy? This is in fact f of xy, because this is the antiderivative. Capital F is the antiderivative of small f, so that's why when we take the derivative of capital F, it gives us small f. Okay, and what is the conjugate of this small f of xy? So remember, this is equal to this velocity vector. So if we can calculate this capital F of xy, which is the antiderivative of the small f of xy, then we can calculate the potential and this psi of xy. Now, what does these functions represent physically? Okay, so we have found this phi, which is equal to v of xy. Now, physically, this phi of xy gives us the equipotential lines. Now, this phi is basically the potential of this vector field, velocity vector field, v. So if we consider a very particular equation, okay, so in the xy plane or the complex plane, if we consider phi of xy is equal to, let's say, c1, then it is going to define a curve in the complex plane, and that curve is basically this curve. Okay, so let's say this corresponds to c1, and similarly, if we take phi of xy is equal to c2, then this is going to give me another function of two variables in the complex plane. It is going to give me a curve, and let's say this is this curve corresponding to the constant c2. And similarly, when we keep on changing the values of constant, then this is going to give me curves, and all of these curves have this property that along these curves the potential is constant of the fluid flow. Okay, so the potential of the fluid flow is constant along these lines. Okay, and what about this psi? Okay, so what does this represent physically in the fluid flow? So this gives us the streamlines. So what are the streamlines? So the lines along which the fluid particles move are basically the streamlines. Okay, now that's how we use our knowledge of harmonic functions to calculate the potential of a given fluid flow problem, and of course we impose some very strong physical conditions on them as well. Okay, so now let's consider a very simple situation, a very simple scenario where the fluid flow is given and the velocity vector field is given to be the following, and of course all the previous conditions that we imposed are valid here. So for example, the flow is irrotational, the flow has no source or sink, and its components are basically have continuous first order partial derivatives, and it is frictionless, and it is incompressible flow. So under all these conditions, now we are going to solve this problem, and in fact we are going to find the potential of this velocity vector field. Now consider v of xy is equal to f of xy. Remember, we need to find this small f of xy, and then we integrate this function f to find the capital F, and then the real and imaginary components of that capital F gives us the potential and the streamline function. Okay. Now let's see what is f of xy in this case. So f of xy is basically the conjugate. Okay. So in other words, this is 2x plus iota 2y. Now remember, this is equal to 2x plus iota y, and if we take, if z is equal to x plus iota y, then this implies this function is basically f of z is equal to 2z. Okay. Now we want to integrate this function to find this capital F. Okay. So this implies this capital F of xy is going to be equal to the integral of this. So this is in fact z square by 2, and 2 and 2 will be cancelled out, so we get this z square. Okay. So this is the capital f of xy, and what are the real and imaginary parts? So the real part is x square minus y square plus iota, the complex part is 2xy. So this is the potential function, and this function is going to give me the streamlines. And so in this case, what are streamlines? 2xy is equal to constant. So this is going to give me the streamlines. And what are equipotentials? So equipotentials are x square minus y square is equal to constant. And of course, when we vary the values of these constants, then it is going to give me different streamlines and different equipotentials. Okay, so if we sketch these equipotentials and streamlines, then it is going to give me the following picture. Now in this part, we discussed a very particular fluid flow problem where our information and discussion of harmonic function helped us in solving this problem and finding, for example, the equipotential lines and the streamlines. Similarly, we can find many examples where this knowledge of harmonic functions gives us solutions to many real-life problems.